Okay, so welcome to lecture number 3. So today we're going to learn about okay. This is the main topic for today. So the quest is the aim, I would say, to compute the ground state energy without solving Schrodinger equation. Okay. That I mean, so without maybe we put our words directly. Yeah, that might be, yep. And so this technique, this method is called the variation principle to get an upper bound condition of the ground state in this way. So where it's not an exact ground state. The function for operator H. Okay. So the question how could we obtain this wave function here? The answer, guessing, yes. There is no system EM way to get this one. You have to guess. That is the thing. If you pick up a good choice, then you will get your answer close to the true ground state of your system. Okay. Now, now I switch to this kind of notation, which I believe that you understand what I mean by this Dirac notation. Okay. Then I don't want to talk about it. Okay. If this is a ground state, then should give you this one. This means that and it's one of the excited state. So you will get this inequality, sure. Okay. This exceed. Of course, because this is not the ground state, then the numerical result will be bigger, right? The actual ground state. Let's prove this statement. So we start by expand this in the state of Hamiltonian operator here, such that you write in this way. So C is a complex scalar, okay? And this is all eigenstate, right? And this is all eigenstate of the Hamiltonian, which then was, yes. Oh, that is a good question. Because we are not going to solve the Schrödinger equation, then you have to start by just plug something into that equation. That is the, yeah, that is the thing, because we do not solve the Schrödinger equation. Yeah. This slide you apply orthogonality, right? And next, so we're going to compute this expectation value of this Hamiltonian. So N. Okay. So you act this to the right, and then you get the eigenstate yeah. So then you have, okay, this one. So since you know that this quantity is greater than or equal to 0, right? This absolute square of this coefficient, and the this condition as well is always is going to be bigger or equal to the Gauss state for the n equal to 0 that you're going to get the Gauss state, right? Then we get so you get this condition since this had to be 1 because this is a normalized condition, right? Right, yeah. So from this, you apply this condition. So you get this inequality, right? And then you apply normalize the probability condition and you get that. And then this is kind of the proof of the statement I put here, okay? Okay, then we'll finish the proof. Next. We are going to consider the stationary condition. Okay. So now, the object that we would like to vary is this one. This state, you do the variation by this mean, right? The state itself parts the value of this state bit by this kind of linear combination, and then you also say that the dual of it can be put in this way. And so we expect that the energy that associated with this state is going to be this one, okay, which is I prefer to put this in this way, okay. So we show that if the state is such that for any small change in function namely this one, then okay. Any extremum in this condition will be the eigenvalue. So let's prove this statement, and then after that I give you an example. Okay, next proof. We start with this E. Okay. And so we know that actually this E is the average of this Hamiltonian, right? Then I put an average, which is okay. Which I did nothing. I was just rewriting thing wrong. Which is for any. Okay. Then with a small chain, as I mentioned over there. So what you're going to have is that you're going to have is a bit cumbersome. We're going to have this, right? If we apply the small chain into this equation, this will be changed by this amount, and the wave function on this bit we will add by this amount, and then on this side we will add this amount. Okay? So it means that so the effect of changing the state in this way, after you apply this Hamiltonian on this state, this will be your new eigenvalue. That is the thing. All right. Okay. So from the left left hand side, you can expand, right, what you could have. Okay, so we have this one, and then we're going to ignore it because it's too small, because you have delta square here, right? We're going to keep only the delta, right? Okay, is that clear from this line? Right. So actually this whole thing is nothing but this one, right? And then you will get that, or the combination. And on the right hand side, what you're going to have is this bit. Again, we're going to throw away this one because it's too delta square too small. Then you get this equation, okay, which is very simple. We find that, okay, so I move to this board. So what we have now is that, so you need to expand these two brackets. So what you're going to have is that okay. This from the left-hand side, right? And we find that, again, the last term, we can throw it away because we have delta square, you see? So we just cross it out. So we are going to keep only the first order of the delta. And on the right-hand side, you have more or less the same. Right, same. And so oh, sorry, it should be. Okay, very good. And we see that these two terms will kill each other, right? Because they are the same. Okay. Right, by this definition. Right. Okay. So now you could solve for this delta expectation value of the h. Okay, so we have this thing, right? So you move thing around to solve for this, right? Okay, you will get that equation. So if is 0, we get this, we have this condition in the case that this delta E, right? This is nothing but a delta E. So you can rearrange things in arbitrary so what we have is that okay, you can rewrite that equation in this way. Can you see that? Because this is a numerical value, so so I would say that yeah, this is very interesting bit. This should apply from the left, right? I know this one should go to the right, and this one should go to the left here, and then you will get these two terms. Right. That it, and then this going to give you these two terms. That is the thing. So now I define a new state. This one. Yeah, it's better to put bracket to make it clear. Okay. So I define this state, and of course that do all of it going to be this one, and we assume that this holds, right? So then this equation can be put in a very simple form now. Okay, yeah. And you say that this delta here can change to this state under this transformation, right? Okay. Okay, these two states link by this kind of transformation. So this going to give you delta here, and this one, right? And give you this, okay? Suppose this is real, okay? So what you have now is that you have two. Okay, this condition. And you find out that this bit cannot be 0. Because if it's 0, then you cannot apply this condition, right? It means that, so this equation holds if and only if this must be 0, right? So it means that this going to be 0. Then, of course, what you have is that here. Okay, we should actually finish the proof, right? So what we want to prove is that, let me make you guys clear again. Yeah. We're going to prove that under the small change of the state, right, with delta E equal to 0, right, that is like a condition that gives you extremum, right, condition. So that state will be your eigen state, right? All right, so let me summarize you a bit here. I don't want to move to over there. Then I give you a summarize here then. So this till that any eigenfunction of H, right, can be found by searching the functional for extremum. Okay. And again, it's not easy. It's difficult tasks to search again. I change the word guessing by use the new word searching. Yeah, but again, it's more like the same. Then there's no systemical way to get the state that you prefer to use. But anyway, that is a kind of you practice enough, you will see how to get the state. Let me give you example. Let's consider this Hamiltonian. The harmonic oscillator, one-dimensional harmonic oscillator. Okay. And so we would like to compute the ground state. Okay, energy by using variation dot. Okay. So we might pick a trial wave function, eigenfunction. All right, like this one. So your alpha is a variation, no, parameter to minimize this energy. Okay. So you need a lot of parameter to take the condition that actually when it is going to give you like a critical condition, right, or extremum, right? So then now it means that your energy going to depend on this parameter. Actually, you know the Hamiltonian, you know the state, you know how to compute this expectation value, right? So actually this bit, I start new board here. It's going to be a huge line. So what you're going to have is that absolute A squared dx, and so we have to turn this to be an operator. Right. Okay. This way. So up to this line, are we good? Okay. Okay, so you just plug all this thing right into the bracket, and then you will get alpha to m omega. Oh, I think I missed the m. Yeah, sorry, guy. We should put the m there. Over 2. Oh no, 8 alpha, and so here. And so this integration can be easily done because it's Gaussian one, right? Then you're going to get this. And so next you're looking for the condition that this one, right? This is critical condition, right? So then what you have is that 0 h bar square 2m minus m omega square alpha square. Am I correct here? I think so. Yes, yeah, right. And then you can solve for alpha, right? The alpha is going to be m omega to h bar. Is that right? I think so. Okay, let's see. Once you get this omega, you're going to plug, back into that equation. Then I would say this for min, right? Or you could call this C, critical, okay? See? Going to give you okay, which it turned out to be, whoa, which is actually the Gauss state, right? Is kind of cheating because actually we know that actually the Gauss state of the harmonic oscillator look like. Then we can guess the function is more or less look like. Then we say that there is a parameter here. Then we can try that actually with throughout this technique, what we are going to get, then we get exactly the same what we have if you solve. If you solve the Schrodinger equation directly, you're going to get this as a Gauss state, right? But the thing is that at this step here is a difficult step. Because the question, how could one know that it's going to be in this form, right? It is your system is much more complicated than this one. Then you have to be in a lucky game. Now, like in this example, we are in a very lucky game. So then we get exactly the Gauss state of the harmonic oscillator, right? Which is EG, right here. Okay, let's see if it gets, if we try to use another type of wave function with exactly on the same system, what going on, with what we will get. Suppose that next we consider a trial wave function this one. Okay. Which should look totally different from this one. Right. But we're going to use that, compute again the ground state energy. Right. So again, this is navigational. Parameter. Okay. So let's check the normalization condition first. Right. If you compute this, you're going to have this one. And so after you do a trick of changing a variable to trigonometrics thing, and then you do the integration, you do find out that actually this is going to give you pi. I'm not going to do the integration for you. I believe that you can do it because it's not difficult, right? It might be difficult, but I think it's not difficult. Okay, so now we solve for the right, to make sure that actually this wave function is normalized, right? Then, now be ready to use this one to compute this expectation value, right? Again, so alpha which is going to give us a very huge, but it's not that difficult to compute, I believe. Okay, so you get this whole integration, and then again you plug thing into that, right? And then what you're going to get is that this so you get this, if I compute things correctly. I think so. Let me think about this. Yeah, no, this is wrong. Okay, and then you put this, right? You could simplify this equation further by using this absolute square of the A, right? You put this, so you will get what you get is that no, it's square. Okay, this one. No, there's a plus sign here. Yeah. Right, and 2 alpha to the third, you get square 4, yeah, 2, 4 m. Yes, okay. And then you get 2 there, m omega. Okay, that's correct, right? Okay. Now, so we're going to look at this again, right? the condition, right? Critical condition.
Second term, we have 1/2.
Which one? You mean this?
Yes.
To there is a pi, right? Let me see. I might. Oh, then it might be a pi here. Otherwise, you cannot. Your pi cannot go away. Sorry. All right. So what we get is that you will get here. So you could solve for the alpha, which is m omega. Right. Then you want to get it, you can say this is your alpha critical, right? You plug into this equation. Oh no, that equation, right? You put in here. So you have alpha square here. So after you put it, you will get square root 2, yeah, which is actually greater than the true Gauss state, right? You see? So by this very example, you see that if you pick a right state, you will get exactly the Gauss state. For any other state, you always get something that actually bigger than the Gauss state. Okay. So you get, this is, again, your Gauss state is the upper bound.
The first term is 1/2 or 4 after the
First term. One, which one? You mean this? Oh, yeah. Right. Thank you. Yeah. Because, yeah, right. You're correct. This should be 2. Otherwise, you cannot have square root 2 here. Okay, very well. So I think you can more or less see how to work with this technique to get the Gauss state of the system without solving the Schrödinger equation, but you have to guess the state that actually a normalized state, right? Okay, that make this condition true, right? Okay. That is the reason why. Can I think of? Huh? Oh, okay. So let me recap again. So you can pick. You have to pick a state that make this condition true. But this condition true by choosing the parameter in your state to make this true. That is the thing. Because if without any parameter in here, you cannot tune. You cannot tune this condition to be true, right? Yeah, that's the thing. So let's move to the next example. Make things much more complex. Let's Any question? Why not x? Oh, well, that's good question because this wave function is a function of x. Then you need an extra parameter. You cannot use the variable.
And if in the wave function we have alpha and beta, it's the same question. If we have much more one.
Right, okay. So it means that so you need in this situation you have only one-dimensional system. Then that's the reason why we need only one parameter. Okay, that's it. Okay, let's have a look at this. Helium. Okay. Okay, so there's a helium atom, which is, you know that from your quantum 101, this is beyond the model that you can solve showing the equation exactly, right? And Hamiltonian is okay. This is Hamiltonian, and we know that the ground state of this system is around this number. This is observation. Okay. I'm going to call this whole term. I'm going to define as VVV interact between the two electrons. Okay. So if we first ignore this term, so you're going to get two independent hydrogen Hamiltonian one. Right. So the ground state of this is I'm going to use this sorry. No, sorry. 100 100 right here. And you know that the ground state of hydrogen atom, right? What is it look like then? It's this where A is the ball radius, right? Okay. A. Okay. With the energy which is around this number. So our goal is we're going to use this as a trial wave function. So we're going to use this as a trial wave function to solve this system. Okay? Let's move to this side. Oh. Then we're going to have this one. Okay, because this bit of energy we get from by ignoring the interaction between the electron, right? Then we could bring it back into this form. So it means that if you compute the expectation value of the system, you're going to get this, right? Okay. Okay. This is the expectation. Is that clear? Right. Okay. Are we cool here up to this point? So the remaining talks is that, so we get this number already, right? At the starting point, the Gauss state of the two independent hydrogen atom at this bit, which is the extra, the interaction between electron, right? Then if you could compute this one, and you could put back into this equation, so you will get the eigen energy that you want, and it's nothing guaranteed that you will get exactly the same, the one that is actually the true minimum here. Let's see what we could get. So now you need to do the integration of this bit. So, well, it's a bit tricky to do this integration, okay? So, okay, so I will left it as a homework for you because it's going to spend a bit time on this. So, but what we get at the end is that after we finish this, you can try yourself and verify yourself when you do the homework whether you get the same that I did here or not. Oh, sorry, it's this one. Yep. So what I did is that I start to eliminate R2 first, and then you left only R1, and then you will get actually this whole integration will give you, if you start from this, going to give you this number. With 4 pi, okay, 4 pi. 4 pi is coming from the angular part, okay? From the radial part, you get this bit at the front. So what you get is that the expectation value of this one is which is this one. Therefore, your expectation value is this one, which is greater than, right? Okay.
Take over I cube, I think is
Square, where is it? A cubed. You mean this one? Square. All right. Indeed, actually. Oh yeah. Yeah. Right, you're right. But you have to check again. But yeah, it should be, yeah, should be 2, yeah. Okay. So by employing or using this Gauss state of 2 independent hydrogen atom as a trial wave function, you're going to get the Gauss state, which is actually quite not that very good, but it's okay, right? Because it's not too far from the real Gauss state. Anyway, this kind of makes sense because it's kind of you ignore the interaction between 2 electrons, then some part of it has been taken away, right? Then you get something bigger. Right. So don't you see any interesting thing here? With this trial wave function, I don't put any parameter in it, right? It means that if I put the parameter in it, I can use that parameter to tune, right, to get a better solution, right? Because now we just use exactly the Gauss state, the product of the Gauss state of 2 hydrogen atoms, right? So to add the parameter, I'm not sure that. So far, there is no parameter. Okay. Well, again, so now we can do that by put this what is a set effective nuclear shot. Okay. Why, you know why it's called effective nuclear shot? What? Because I just delete the picture because do you know that actually the charge of the nucleus is 2, right? And by use this word effective, it means that it might not be 2 in some situation. Why is that, you know, at the Gauss state? The Gauss state is actually depends on the radius and the radial, right? Radial part, no angular part, right? So it means that so if this is your nucleus, so one electron may be forming a shield, right? It's called shielding effect, right? right? Then totally, then is partially reduce, right, the charge of this nucleus, right? Okay. Then the Hamiltonian for this system can be put okay, it's going to be this one. So your expectation value is going to be one. So this going to be this one. So you could think that actually this is like a one particle situation, right? Then you can just, they are the same. Then you get two of this. And expectation value of this interaction. Well, so to compute this, you just applying this, right, with this parameter right here, and so what we're going to get. So I skip a lot of the math, but I believe it's not difficult to follow later by yourself. You're going to get this one. And so again, okay, this one, right, with this one. So, and here, you will get, so it's a long computation, but I believe that you can do it later by yourself. If I'm too lazy. Okay, so you will get this bit, okay, and then what we have, okay, so too long computation actually. Okay, which it actually can be simplified. Into this, and so we're looking at the critical condition, right? This is the critical. Think about the question about your question why we do have only one variable here. Interesting. It's nothing to do with the dimension, right? from this very example. So if you apply this, you will get which, okay, then what we have here, okay, whoa, which is better, right? Better, right? We improve by put the parameter in the trial wave function in this way, and we get you see at the first step if you just use a regular trial wave function from the two independent hydrogen atom, you get this number, but this one is getting closer, right, with the parameterized variable here. Okay, so that's it. The question why we have only one parameter here, can you think about that answer you asking me before? Because we have only one quantity to minimize the energy, right? No. It must be some a parameter in your system, or you can add it by hand into your state in order to apply this condition. But for in this situation, we go we it's a bit cheating because we know that actually this is the state of two independent hydrogen atom, right? And then we just put the effective charge of the nucleus in there to be like the parameter, then we just do it again. The question is that if you get some other type of function, you will get totally different number of here. Like in the harmonic oscillator I will give you, if you start from the exponential function, you will get like exactly the same with the Gaussian, but if you start with the ratio of that polynomial of x squared plus alpha squared, then you will get something different. So I will give you more question to practice to get. I'm not sure yet. Let me think that in the homework I should give you a system and then you could guess yourself the wave function, or I could give you a trial wave function and then you can use that to compute the energy of the system. Let me think about that. That would be all for today. This is a kind of technique of variational principle. So I'm going to recap you guys again, is that this technique is used to compute the ground state energy of the system without solving the Schrödinger equation directly. So it means that you have to guess the state, right? That makes this condition false. That is a thing. Okay. And that's it. And of course, there is some other example. There are plenty of examples in the internet, in the books as well. And so you could have a look at that. And I'm going to give you homework for that. And I might need you to repeat all this step by looking in detail how to do the integration of this, because I think you need to understand more or less by yourself to make sure that actually you can do the integration. Otherwise, then all right, then that's all for today. Thank you very much. Then see you next class.